Let's take a look at a related rates problem that is just one layer of extra thinking on top of what we've been doing so far. All right, so here we have water leaking out of a cylindrical tank at the rate of 3 cubic feet per second. If the radius of the tank is 4 feet, at what rate is the depth of the water changing at any instant during the leak? All right, so once again, let's visualize this problem for a second, just so we can think about it. So I've got some sort of cylinder that's got a constant radius. The radius of the cylinder isn't changing, but as the water is flowing out of it, the height of the water, or the depth of the water, however you want to think about it, is lowering. And so we want to compare the volume of the water to the height of the water, and then calculate the change, the relative change of both of those factors. All right, so we want to identify all of the variables in the problem. And so we've got, I'm going to call it height instead of depth, just because height of a cylinder is something that we're a little more familiar with. And V is volume. And so we want to identify the variables that remain constant. So that's a little bit of an oxymoron. If something is variable, then it's not constant. But what they're talking about here is that we're talking about a radius, and the radius of the cylinder isn't changing over the course of the problem. All right, and so let's talk about the rates that are given and the rate that we wish to find. All right, so what is the rate that's changing in this problem? Well, we've got water leaking out, 3 cubic feet. So cubic feet is a unit of volume. So we've got dV dt is equal to +3 or -3? Water is leaking out, so let us represent that change, that decrease, by calling the rate of change -3. And what we want to change is we want to calculate the rate of change of the depth of the water, which I'm calling dH dt. So what is the equation that relates height and volume and radius of a cylinder? Well, we can check our geometry reference sheet if we're confused about it, but the volume is equal to pi times r squared times h. So it's the area of the base of the cylinder times the height of the cylinder. Okay, and so since we've been told that the radius is staying 4 throughout the problem, why don't we just substitute 4 in for r right now? So that's pi times 4 squared times h. So volume is equal to 16 pi times h. And once again, what they're saying here is that this had 3 variables in it: volume, radius, and height. But after we had done our substitution, we only have 2 variables, which is cool because we've got 1 rate. If we had 1 rate and 3 variables, we wouldn't be able to solve this problem. But now that we've got this like this, we can implicitly differentiate the specific volume with respect to time. And so that's dV dt is equal to 16 pi times dH dt. And now we can substitute in what we know. We know that dV dt is equal to -3. So we've got -3 is equal to 16 pi dH dt. And then we divide through, and so we get dH dt is equal to -3 over 16 pi. All right, so once again, we'll grab our calculator. And so -3 divided by 16 divided by pi is equal to -0.06, well, 0.597. I'm going to give 3 significant digits there. So as I say, AP problems like to see 3 3 decimal points of precision, but if you want to add extra, there's no penalty for doing so. All right, and what is the units we should have for this problem? Well, this is dH/dt, the change in height over time. So we're measuring height in feet, and we're measuring time in seconds. So this is feet per second. Does the fact that our answer is negative, does that cause us concern? Or does that make sense in the context of this problem? So we've got water coming out of a tank. So as water is coming out of a tank, it makes sense that the height is decreasing over time. So a negative change in height is exactly what we would expect to see. And what we see in this problem is that we can see that the rate of change of the height is constant. In the problems we did before, the change might depend on some extra factor like the radius. But we can see that since this is a cylinder, at every moment in time, the height is going to decrease at a constant amount because the water is flowing out of the tank at a constant amount and the radius of the tank isn't changing. Okay, so that's something where it doesn't surprise us that dH/dt is something that didn't depend on something like the radius or the height at that specific moment in time. In the next problem, we're going to take a look at a slightly harder geometry related rates problem, kind of the star problem that we have when we talk about related rates. And once again, you'll see why when we get to the next problem.